Okay, let's work on graphing this rational function. So let's first start with the domain. What kind of x values can I plug into this? Where on my xy plane is this function going to exist? So I have a polynomial divided by a polynomial, so I can stick any real number that I want into either of those two polynomials and I'll be fine. The only problem is what happens when I divide by zero? What's going to make my denominator equal to zero? And because my denominator is already in factored form, I can just read off the zeros immediately. Right? If x is equal to minus 6, that's going to make that term 0, right? Minus 6 plus 6 gives me a 0, right? This one tells me x cannot be 3. This one tells me that x cannot be minus 1. So from the factored form of my denominator, I can see that the domain is going to be all real numbers, except I need to skip minus 6, minus 1, and 3. All right, now let's take the function and write it in simplified form if possible. So we have x plus 6 in the numerator. My denominator was already in factored form, so I can't break that down any further. But I am able to break this quadratic into two smaller factors, right? I can write that as x minus 3 times x minus 3, or x minus 3 squared. So then I can see that this simplifies quite nicely. The x plus 6 cancels with one of those, and the x minus 3 squared cancels with that x minus 3 squared. So I'm left with x over an x plus 6 and an x plus 1. So I was able to remove the discontinuity at x is equal to 3, and I only left with non-removable discontinuities at minus 6 and negative 1. So let's go ahead and locate those. When x is equal to minus 6, 1, 2, 3, 4, 5, 6, I have a non-removable discontinuity, so I've got a vertical asymptote right there in my graph. I'm not allowed to cross this line, so I'm going to denote that with a red dashed line. I also have a non-removable discontinuity at minus 1. So again, we have a vertical asymptote here. Okay, what else can we use? Let's look at the end behavior of the function. So the end behavior is going to be dependent upon the degrees of the numerator and the denominator. So let's go back up. I can use my simplified version of the function here, or I can use the original version. I can use either one, because if I took a 0 out of my denominator, then I had to take a 0 out of the numerator as well, right? So the ratio of the degrees will be the same in either case. So if I look here in my simplified version, I have a degree 1 on top, right? There's 1x right there, over a degree 2, there's 2x's in my denominator. So the denominator is more powerful than the numerator, so this function is going to drag to 0 as x's get larger and larger. Right? So as I move either towards negative infinity or towards positive infinity, the function is going to decay towards y is equal to 0. Right? The bottom of the fraction gets larger faster than the top of the fraction does. So the entire value of the function is going to approach 0. So I know that as I move away from the origin, that I need to get closer and closer to that green line. Okay. Now let's talk about intercepts, right? We can use intercepts to give details to graph. In fact, let me finish this. We have a horizontal asymptote at y is equal to 0 by looking at the comparison of the degrees. Now let's look at x-intercepts, right? These are another name for the zeros. What's going to make my function give me a 0, right? This is the question that I'm asking. When does my function give me a 0? Well, the simplified version of my function is x over x plus 6, x plus 1, And I can multiply both sides by that denominator, and this just simplifies quite nicely to x is equal to 0, right? Anytime I have a fraction equaling 0, I know that the numerator has to be the thing that's equal to 0. So I have a 0 at x is equal to 0. So I'm going to go ahead and go up to my graph and plot a point right there, right? My x-intercept is x is equal to 0. Now we could also think about y-intercepts. Y-intercepts, remember, what does your function give you as 0? Right? When your function is 0, when are you going to cross this y-axis? Well, we've actually already figured that out, right? That's the point that we cross our y-axis at. So there's nothing else to do. If you set your function r of x, or rather, if you plugged 0 in for x into r of x, you get 0 over a 6 and a 1, right? That's just 0. We already knew that. All right. Now, what else can we use here? I think we're ready to plot a point. So I need a test value because I can't use this test value, right? I know that's a point on my graph, but I don't know if I move to the right, if I'm going to go downwards or if I'm going to go upwards. Right, so I need a test value here. So let's look at what happens at 1. Right, 1 is inside the domain of my function, so I can evaluate it. What is r of 1? So that is 1 using that function, that form of the function, 1 over 1 plus 6, 1 plus 1. That gives me a 1 over 7 times a 2, or 1/14. So when x is equal to 1, the y value is 1/14, right? It's just barely above the x-axis there. But that's everything that I need. So I'm going to put my pencil right there at that point. And as I move in this direction towards the right, I know that I need to approach my horizontal asymptote because that's my end behavior. I also know that I don't ever cross this horizontal asymptote, right? I only cross right there when y is equal to 0, or rather when x is equal to 0. So the behavior of my function, if I start here, has to do something that looks like this, right? As I move to the right, it's going to get infinitely close to that horizontal asymptote, that green dashed line there. Now, if I put my pencil back at that point, and now I move in the leftward direction, what's going to happen? So I have to hit my 0 right there. And because of the multiplicity of that 0, right, look at this form, this simplified version of your function, that 0 occurs once in your numerator. So because of odd multiplicity, you're going to pass through it, and consequently, you're forced to approach that vertical asymptote from the right as you move towards negative infinity, right? You got to go downwards there. Now, what is the multiplicity of that vertical asymptote? That vertical asymptote happens at -1 and is a consequence of the x plus 1 factor in your denominator right there, right? That factor occurs once, so it has odd multiplicity. Therefore, your behavior will do opposite things, right? If you go down towards -infinity on the right side, then you have to go up towards positive infinity on the left side. Okay, now as we travel downwards, you're not allowed to cross your x-axis again, right? You only cross at the origin. So with that in mind, we have to do a U-turn, and we approach the vertical asymptote at -6, also traveling towards positive infinity, traveling infinitely upwards. And again, by multiplicity of the asymptote, I can find what I'm doing on the other side of that. So the multiplicity of that asymptote, the asymptote at -6, a consequence of this x plus 6 factor, that factor occurs once, so the multiplicity is 1. It's odd, meaning that I have opposite behavior. So I know that I'm also going down towards minus infinity on the left side of that asymptote, right? If I'm traveling towards positive infinity on the right side, then I have to travel towards minus infinity on the left. All right. So as I keep going further and further to the left, I know I don't cross this horizontal asymptote, right? I only cross it at y is equal to 0. So I'll approach my horizontal asymptote from below, and I'll get infinitely close to it as I move to the left. Okay. We have one more thing to do, right? In the beginning, we told ourselves that our domain was all real numbers except -6, which we have a non-removable discontinuity there. So we've already taken care of that. Our function doesn't exist there. We also have a vertical asymptote at -1. We've already taken care of that. But I'm also not supposed to exist when x is equal to 3, right? That's not in my domain, because if it was 3, then that term would make me divide by 0, but I was able to remove it in my simplified version. So I just have to remove that part of my function. So I locate x is equal to 3. And I have an open circle right there, a removable discontinuity. All right, and this is a pretty decent idea of what the graph of that rational function is going to look like using only algebra techniques. So hope you found this helpful.